In this video, we're going to introduce what the book refers to as the Fundamental Theorem of Calculus, Part 1. So we'll start with a definition. Given a function, we'll call it g. Its definite integral function finds the area below g. So with that in mind, the notation that gets used for a definite integral function would be something like f of x is equal to the definite integral from a starting point to a specific value of x. Now normally for a definite integral we would expect to see something like g of x times dx in here, but unfortunately we've already used x for a different purpose, so we can count on seeing a different variable as part of the definite integral. As an example of this kind of function, let's consider f of x is equal to the definite integral from 0 to x of 2t times dt. So essentially what this is saying is we'll take the function y equals 2t, and we are going to calculate the amount of area that's underneath here. Now, good news for us is that the area in this case can be interpreted as the area of a triangle. So what I'm going to do is calculate several different values by plugging in values of x, and then calculating the corresponding area that would be underneath the curve. Now, using a property of definite integrals from the previous section, if I plug in x equals 0, we would have the definite integral from 0 to 0, and as soon as we have the definite integral from 0 to 0, it doesn't really matter what the rest is. Now for 1, that would indicate a base of 1 and a height of 1. A base of 1 and a height of 2 by plugging it into the function. So this would be 1/2 times the base times the height, which when simplified would give us 1. If I plug in x equals 2, that would give us a base of 2 and a height of 2 times 2, that would be a height of 4. So 1/2 the base times the height would be half of 2 times 4, which would be equal to 4. If I plug in x equals 3, the base of the triangle would be 3, the height of the triangle would be 2 times 3. So that would be 1/2 times the base times the height, which is equal to 9. Now what you may notice is that there's a bit of a pattern going on here, that generally speaking, if I'm plugging in x, we wind up with 1/2 times a base of x times a height of 2x, which simplifies to be simply x squared. Now this is related to the other function in the form of, if I were to differentiate x squared, I would get 2x, which is essentially the same function as what we had up here, just with an x instead of a t. This helps motivate what is known as the Fundamental Theorem of Calculus, Part 1. The Fundamental Theorem of Calculus, Part 1, states the following. If f of x is equal to the definite integral from a starting point up to x of g of t dt, then the derivative of f with respect to x will be equal to, take the original function and simply replace the t's with x's. Now, if I understand young people the way that I think that I understand young people, I believe this would be the proper notation that we use in a case like this. Get that t out of there and yeet an x into there. Hopefully that makes more sense. So for some elementary examples of the fundamental theorem of calculus, let's consider the following. Let's say that f of x is equal to the definite integral from 1 to x of the sine of t divided by t dt. If I wanted to differentiate this function, it would simply be a matter of replace all of the t's in this function with the x that you see up here. As long as the lower bound is a constant and the upper bound is just the independent variable, you're allowed to do this. We'll see some more examples in just a little while. I do, however, want to go over the proof of the fundamental theorem of calculus, part 1. So we had our definition of f of x being the definite integral from a to x of g of t dt. I'm going to draw a picture of this situation. Here's y equals g of t. Here's our starting point a, and here's a value x right over here. The area that we would get here would be equal to f of x. Now, part of taking a derivative is going to be taking the limit as h goes to 0 of f of x plus h minus f of x all over h. So what I'm going to do is demonstrate what would f of x plus h then look like. It would be the definite integral from a to x plus h of g of t dt. Meaning that if I were to go just a little bit farther out here and call that guy x plus h, then that would be all of the area up to that boundary. Now what this also means is that if I were to take f of x plus h minus f of x, I would be talking about just this little strip of area right here. Or using the properties from section 5.2, that would be the definite integral from x to x plus h of g of t dt. Now we're assuming in here that h is going to wind up being very, very small. In fact, this width is going to become infinitesimal when that takes place. So what we're going to do is make an approximation. This is going to be approximately equal to the area of an approximating rectangle. The area of the approximating rectangle, we'll use a left endpoint for this. The length of the base is a little tiny change in x, which in this case would be x plus h minus x. That'll be h. For a left endpoint, that would be taking the function g and plugging in x. Which means that if we were to take f of x plus h minus f of x all over h, this would be approximately equal to simply g of x. This becomes exact when h goes to 0, which means that f prime of x, which is the limit as h approaches 0 of f of x plus h minus f of x all over h, that's going to be exactly equal to g of x. And that completes my proof.